we are going for the last reaction, which is oxidation of cyclohexanol. Okay, now we are going for the opposite reaction. Now we have cyclohexanol. Again, cyclohexanol, they can be axial or they can be axial alcohol, equatorial alcohol. दोनों प्रोडक्ट मुझे सेम देने वाले हैं, इसका ऑक्सीडेशन करो या उसका ऑक्सीडेशन करो, आई एम गोइंग टू गेट द सेम प्रोडक्ट. But now previous reaction was to predict which alcohol is formed. This reaction is about which alcohol will react faster. Whether actual alcohol will give me the faster reaction or whether it is equatorial alcohols are going to give me the faster reaction. Okay. Again, oxidation के लिए हमारे पास अलग अलग reagents available है. फिलहाल हम लोग सिर्फ एक ही reagent के बारे में बात करेंगे यहाँ पे, that is chromic acid. Okay. So now generally how this reaction take place, let us understand. So let's say I have this alcohol here. Okay, this will react with the chromic acid. I'll just draw the structure of chromic acid. So this is Cr, double bond O, double bond O, double bond O. Okay, so lone pair will be shared with the chromium. Okay, this will become OH. Okay, so this is chromate ester in short. Chromate ester is formed in this reaction. Okay, and finally when this reaction will happen, I'll just draw here one proton so that यहाँ पे ठीक है, और यहाँ पे मैं प्रोटॉन एब्स्ट्रैक्ट कर, ठीक है. So finally this oxygen, see this is particular, it is lost, and then finally this will, the water molecule will abstract the proton from this carbon so that I will have double bond between the carbon and oxygen. Okay, so जैसे ये proton abstract हो जाएगा, okay, this proton is abstracted from here, so this will give electron to this between the carbon and oxygen, तो यहाँ पे double bond form होगा and this will leave, so your chromate acid will be lost from here and I will end up with the formation of the aldehyde or ketone depending on what type of reagent you have. So here there are two steps. First step is formation of this chromate ester. Okay, chromate esters are formed. Okay, and step number 2, abstraction of proton. Okay, now if I draw this mechanism with the help of the cyclohexane derivative, how, what kind of approaches will be possible? See, first approach, let us talk about the axial alcohol. Here there is a proton. Okay, now this will be attacked by the chromic acid and then I will end up with a chromate ester here. This is OCr and this is H. Okay, and then here step 2 will be water will be abstracting this proton, and as this proton will be abstracted I will end up with the cyclohexanol. Similarly here also this is OH, chromic acid. So here the ester will be formed and then proton will be abstracted I will end up with the same product. Okay, So now in this case, it has been seen that your actual alcohols are reacting faster. Okay, ये result है मेरा जो मुझे regular मिला है. Okay, regular result I got, that is actual alcohols are reacting faster. So now then they decided, let us discuss now how we are getting the, or why the actual alcohols are reacting faster. Previously it was considered that this what approach of water to abstract the proton is your rate determining step, because in this case, in the actual alcohol, can you see where the water is approaching? It is approaching from which side? It is approaching from equatorial side. Whereas in the second case, water is approaching from axial side to to remove that proton. Which approach is easy for water, to remove the proton from the equatorial or to remove the proton from the axial?
Ecuadorian.
Equatorial.
Equatorial. And that's why according to this step, it was considered, this is a step which is giving us the idea that why the actual alcohols are reacting faster, because water, for water, approaching the equatorial side will be easy, and to remove that what oxygen, sorry, hydrogen will be easy. Okay, but later on it was found, they tried this reaction with the different steroid derivatives, and uh, in alcohol, actual alcohols only, actual a different type of alcohols they have taken, and what they have seen that removing proton from the axial position or with the equatorial position doesn't make that much difference, because they tried with the different derivatives, and what they found, when the proton is removed from the axial location and the proton is removed from the equatorial location, for these type of reaction, the rate was almost found to be same. Therefore later on they focused on step number 1. Now if you look at the step number 1, step number 1 is talking about, so this is not the deciding factor. Initially it was considered as this was the deciding factor, then later on they focused on step number 1. Now in look at the step number 1, in the first case the chromate ester is formed. Look at the chromate ester. Here it is at axial location and here it is at equatorial location. Which chromate ester is stable? The first one or second one? Second is stable. So now first one, don't you think so? Since it is unstable, here the water will easily approach. So that this instability, chromate, when the water will approach, the chromate will leave, na? Of course. So if this is unstable, it will try to get stabilized faster, and therefore the axial chromate will react faster compared to the equatorial chromate, because axial chromate ester is unstable, so it will try to get stability by abstraction of that water. तो इसलिए ये जो actual alcohol है, that is reacting faster compared to equatorial alcohol. What is the reason behind this? The actual reason behind this is the axial alcohol gives us the formation of axial chromate ester. An axial chromate ester is unstable, it will be try to react faster to give me the stable product.